Good evening, class. My name is Seth Murray, and today for our discussion for Module 7, I will be going over Homework 7.2, Problem 10.29. So first things first, a little overview of a problem. Here you can see we have a T-beam with pre-filled dimensions that I pulled from the homework problem. And it's asking us to, one, determine the centroidal Y position, which locates the centroidal axis, X, for the cross-sectional area of the T-beam. Part B and C is asking us to determine the moment inertia along X and Y. So first things first, let's go into Part A. And Part A, I went ahead and I have the graph already made to save time. But to sum it up, this graph is telling me that, hey, look, this T-beam, it's too complex to do in one part. So I need to break this beam up into two parts. My first part will be this vertical rectangle. And my second part is going to be this horizontal rectangle. And I'm going to label this one Part 1, and I'll label this one Part 2. So let's go ahead and get started. So area for Part 1, which is the horizontal rectangle. Pretty straightforward. It's going to be 20 millimeters times... Oh, shoot, my math sucks. 150. So 20 times 150. That's going to give me, for area 1, 3,000 millimeters squared. Okay, so my centroid for area 1, along the y-axis, mind you, is simple. It's very straightforward. I have this 20 for my height of C. All I need to do is to find the centroid of this horizontal beam in this y direction, which is just 20 divided by 2, which will give you 10 millimeters. And then for my YA, all I have to do is multiply my centroidal Y by the area, and that'll give me 30,000 millimeters cubed. Make sure everything's copacetic. All right. Moving on to area 2, this area right here. My vertical rectangle. Area, same thing, easy. 160 millimeters for the height and 20 millimeters for the width. That'll give me a total of 3,200 millimeters squared. For my centroid, all right, here's where it gets a little tricky. So my centroid for this vertical rectangle is going to be 160 divided by 2, right? But that only gives me part of the answer because I need to take into account that this dimension is from the top of this T-beam. So I also need to add 20 millimeters to this problem. So I know that 160 divided by 2 is 80, right? Next, I'll add the 20 millimeters, and that'll give me a total of 100 millimeters for my centroid. Because that's saying for this rectangle, from the top here to here is 100 millimeters. All right. So next, I'll just multiply 100 by 3,200, and that'll give me 320,000 millimeters cubed. Sorry, I am a mess. Move that down, more appropriate. All right. So now, next, I need to sum up my area, and I need to sum up my YA. So pretty simple addition. 3,000 plus 3,200 is 6,200. 30,000 plus 320,000 is 350,000. So in order to get the total centroidal Y location, I have my formula here that states that the sum of YA over the sum of A will equal my overall centroidal Y location. So I'll take the totals that I already calculated, which is 350,000 over 6,200, and that'll give me a total of 56.5 millimeters. So that is the answer to part A. And this 56.5 is this dimension here. All right, next is part B. So part B is I need to determine the moment of inertia. So like earlier in part A, I broke my T-beam into two parts, and I also need to do the same here. So I've labeled it horizontal and vertical just for frame of reference. I think it's pretty self-explanatory. So first up will be my horizontal portion of the T-beam. So for moment of inertia prime, I need to plug in these three I need to plug in these three sums: moment of inertia, area, and differential distance. Well, my moment of inertia, I know from class, from our book, from our cheat sheet for our tests, I know that our moment of inertia for a rectangle is 1 over 12 base times height cubed. Okay? Plus area, not going to change. And then my differential distance is not going to change either. All right, so I'm going to go ahead and plug in my numbers that I know are my base and my height for my horizontal beam. So 1 over 12 base is going to be 150 millimeters, and my height will be 20 millimeters cubed. Don't forget that. Plus the area is 3,000 millimeters cubed, squared. And now my differential distance is going to be my centroidal Y that I got here minus 10 millimeters, which is the centroidal Y for the horizontal portion of the bar. And then square that as well. And this is going to give me a total of a large number of 6,586,750 millimeters to the fourth. So that's for the horizontal beam for part B. Now I'm going to move on to the vertical part. Same concept. It's not rocket science. I'm going to go ahead and plug all my numbers in. 1 over 12. Base for that will be 20 millimeters times 160 plus the area, which is 3,200 millimeters cubed, and then 100 minus 56.5. So that's going to give me a total of 12,867,000 millimeters to the fourth. All right, so that's for those. And now I've got everything I needed to determine the moment of inertia for x. Just need to do some basic math. So I'll take my first number, and I'll take my second number, and I'll just add. And this will give me a total of 19.47 times 10 to the sixth millimeters to the fourth. And that's going to be my moment of inertia for x. All right, that's part B. Finally, part C. Don't think I need to go into it too much. With these being two rectangles, everything's pretty much going to be, the setup is going to be different in terms of what your base and heights are because it's in relation to y, but the formulas are the same. So I'm going to go ahead and just plug all this in real quick. I don't think I need to explain that. So 1 over 12 base is 20 times height is 150 cubed, and that equals 5,625,000. And then for this one, 1 over 12 base is going to be 160. Height is 20 meters cubed. And this is going to equal 106,667 millimeters to the fourth. All right. And then you guessed it, same process. Adding together my totals for the vertical and horizontal. And that's going to give me a grand total of 5.73 times 10 to the sixth millimeters fourth. And that is my moment of inertia for y. Thank you for listening. I appreciate it. If you have any questions, feel free to email me.